Given an integer matrix, find the length of the longest increasing path. From each cell, you can either move to 4 directions, left, right, up, or down. You may not move diagonally or move outside of the boundary. This is the matrix from the first example. I and j represent row and column index. To break down this question, let's first do a simpler version of it, which is finding the longest increasing path for a given starting position I and j. The longest increasing path starting at position I and j is either 1 if there are no surrounding positions containing a higher value, or 1 plus the maximum of the longest increasing paths starting at surrounding positions that do contain a higher value. Let's go through an example using the starting position I equals 1 and j equals 0. The value at this position is 6. Looking in the 4 directions, only the 9 at position I equals 0 and j equals 0 is greater than 6. So the longest increasing path is 1 plus the longest increasing path starting at position I equals 0 and j equals 0. This turns out to be 1 since there are no surrounding positions greater than 9. Let's try this on another starting position I equals 1 and j equals 1. Here, both the 9 and the 8 are greater than 6, so the longest increasing path is 1 plus the maximum of the longest increasing path starting at either I equals 0 and j equals 1, or I equals 1 and j equals 2. Both of these evaluate to 1, so the longest increasing path starting from I equals 1 and j equals 1 is 2. To find the answer to our original question, we can just find the longest increasing path for all possible starting positions. One problem with this solution is that we will have repeated function calls, which will be computationally expensive. For example, let's compute the longest increasing path starting at position I equals 2 and j equals 0. Looking at the surrounding positions, only the 6 at position I equals 1 and j equals 0 is greater than 2. So the longest increasing path becomes 1 plus the longest increasing path starting at I equals 1 and j equals 0. We've already done this computation before, so we'd like to avoid having to do it again. To overcome this problem, we can use memoization. This means optimizing the solution by caching intermediate results to avoid having to repeat the same computation multiple times. We can create a new matrix that will store the longest increasing paths for each starting position. At first, this matrix will contain all zeros. Each time a longest increasing path for a position is found, we will remember the result by storing it in this new matrix. Each time we want to get the longest increasing path for a position, we will first check its value in this new matrix to see whether it has been computed already. To see how this works, let's again get the longest increasing path starting at I equals 1 and j equals 0. First, we look at the value at this position in the new matrix. The value is 0, which means that we haven't done this computation before. So we search the adjacent positions for a higher value. The 9 at position I equals 0 and j equals 0 is higher, so our longest increasing path now evaluates to 1 plus the longest increasing path starting at I equals 0 and j equals 0. Again, we first look at the new matrix, but now at position I equals 0 and j equals 0 to see if we have computed it before. The value is also 0, so we search the adjacent positions for a higher value. There aren't any positions with a value greater than 9, so the longest increasing path starting at position I equals 0 and j equals 0 is just 1. Now that we have found this result, we will store it in the new matrix at position I equals 0 and j equals 0. We can resume computing the longest increasing path starting at I equals 1 and j equals 0, which evaluates to 2. Again, we will store this result in the new matrix at position I equals 1 and j equals 0. Next, if we wanted to get the longest increasing path for position I equals 2 and j equals 0, we first look at its value in the new matrix. The value is 0, which means we haven't done this computation before, so we search the adjacent positions for a higher value and see that only the 6 at position I equals 1 and j equals 0 is larger. So the longest increasing path starting at I equals 2 and j equals 0 becomes 1 plus the longest increasing path starting at position I equals 1 and j equals 0. Now when we try to evaluate the longest increasing path starting at I equals 1 and j equals 0, again we first check its value in the new matrix. The value at I equals 1 and j equals 0 in the new matrix is no longer 0, which means we have already done this computation. So we can just plug in the number we previously stored. Finally, we can resume computing the longest increasing path starting at I equals 2 and j equals 0, which is 3. Again, we will store this result in the new matrix. Now let's implement this logic in Python. First, we define a function called longest increasing path that takes in an argument matrix. If the matrix is empty, return 0. M and N are the number of rows and number of columns. Here we create the new matrix filled with zeros. Next, we'll define a function called longest path that takes in two arguments I and j, which represent a starting position. First, we check the value in the memo matrix at position I and j. If the longest path at position I and j has not previously been computed, we create an empty list that will contain the longest increasing paths for surrounding positions that contain higher values. To do this, we iterate through each adjacent position. For each adjacent position, if it is bounded within the matrix and contains a higher value, we'll compute the longest increasing path at the adjacent position and append it to the adjacent paths list. After the for loop ends, we find the longest increasing path starting at I and j by evaluating 1 plus the max value in the adjacent paths list. The default equals 0 argument tells the max function what to return if the adjacent paths list is empty. This result is stored in the memo matrix. The longest path function ends by returning the value at position I and j in the memo matrix. Finally, to get our answer, we use this longest path function and apply it to all possible starting positions in the matrix and return the max value.